Okay, so we are looking at electrical work or work done in an electrical system. I have both worksheets here. We're going to look at some problems, see if we can kind of pinpoint some that might give you a little bit of difficulty. So follow along and we will tackle some of these problems. So on the front here, we're just looking to do a little bit of reading and understand a little bit more about electricity in general. So the big idea, voltage and current and charge. So current is how fast electricity is moving. So it's usually current is in amps, and 1 amp is equivalent to 1 coulomb per second. All right, so 1 amp equals 1 coulomb per second. Okay, so that tells me how fast it's moving. All right, because it's usually charge with time. Okay, so kind of some of these other ones, a coulomb here. So remember we talked about that in class. That's 3.65 billion electrons. So it's a pretty big amount, and we figured out how many times it would fill our classroom. Okay, so next one we're going to kind of write this down. Define the equations for, or write equations for electrical work. All right, so we have work equals volts times charge. And at this point in time when we work through this worksheet, we don't know the other equation, but we learn it. So the other equation is work equals volts times amps times time. So these are the two equations for electrical work, and we could rewrite those if we wanted to, but that's the way we're going to leave them for now. All right, so let's jump to number 9 here. When figuring efficiency, which is always less, work in or work out? And if we remember, it's work out over work in. So we always have an efficiency of less than 100%, so that means our output is going to be less than the input. Okay, and if we're talking electrical work here, electrical work is usually the input. Okay, so let me fix that here. Electrical work is always the input because that's what we're putting in to the system to get something out. So that's work in. Okay, so that's what we're putting into the system to get our mechanical work out. And then the reason why we use electricity to do work, it's efficient. We can turn it into several other forms of work. So we can turn that into fluid work. We can turn it into mechanical work. We can use it quite a bit. All right, so let's look at some problems involving that. So if we kind of just remember our equation, work equals volts times charge. Okay, that should be what we're using for most of these equations here on the first worksheet. Okay, so this one, generator transfers 1 coulomb of charge through a potential difference of 110. So we got work equals volts is 110 times charge, which is 1 coulomb. So that's just 110 joules. Okay, so what's the potential energy of 1 coulomb charge after the transfer? So that is 110 as well. Okay, so the generator is doing 110 joules of work, and it says what's the potential energy of 1 coulomb of charge? So the potential energy and work are essentially the same thing, so this is just rewording that. So again, that's 110 joules. Okay, so both of those are 110 joules. Okay, so kind of reading down here, we got volts in charge, we got volts in charge. All right, so down here with that 50 volts and 100 or 50 coulomb, excuse me, and 110 volts, what work does the generator do? So we can kind of look at this one. It's got a little bit of a extra piece to it, so that time component for part B. So we have, let's write our equation again, volts times charge, and we have 110 volts. times 50 coulombs of charge. Okay, so then we do 110 times 50, and I think it's 5,500. Let's double check. Yep, so 5,500, and again that's joules. Okay, so 5,500 joules of work, that's our electrical work done. And now for this part it says it accomplishes this work in 5 seconds. How much is done per second? Well, if we have 5,500 joules, and that is done in 5 seconds, we just divide those two, and then we're going to get 1,100 joules of work per second. So we want joules per second. Okay, so that's how much we're doing per second. Okay, so this one we have joules of work, and then we have coulombs of charge, so that one's slightly different. But when you plug stuff in, it shouldn't be too bad. So we have 120 joules of work, and then that goes with volts. We don't have that, times charge, just 1 coulomb. So this one's pretty easy. How do we get rid of the 1 there? We just divide both sides by 1 coulomb. And gone. 120 divided by 1, that's just 120. So we have 120 volts. Oops. 120 volts. Okay. So number 6 is more of a conceptual question. There isn't really some math involved here. But in Europe, electrical outlets are 220. In America, they're 120. What happens if a tourist from North America took an electric razor to Europe and plugged it in an outlet? Well, that razor, okay, that electric razor, let's say E-razor, that's used to the 120 volts. So everything inside of that razor is made to accommodate 120 volts. So the resistors, the motherboard, the little computer in there, I guess I don't know if there's much of a motherboard. That's usually an on or off switch. That little motor in there, okay, that motor for that razor is built to withstand or to use 120 volts. So if we're trying to pump 220 volts in there, that's almost twice as much voltage as the thing is used to, so that's going to burn out the motor. It's going to ruin the electrical components in there. So that razor would be fried. Okay, so we're looking the other way now. So if somebody from Europe brought a razor to North America, so they're using 220 volts, and we're trying to use 120 volts to power that, then it's either not going to work, or it's going to be it won't have enough power. So think of it like you have, let's fix it. Think of it like you have I don't know, your phone. Nah, your phone would be a bad idea. Think about something you put 2 AA batteries in. What happens when the AA battery starts to go dead? Then it starts to go slow, right? So it's not going to be as efficient as normal. Okay, so last one here, electrical space heaters are manufactured in a variety of different designs. When purchasing a heater, what information should you look for to decide if it will adequately heat your area you have in mind? Okay, well that would be, this is kind of a different question, but first of all, if you are inside or outside, we have 120 volts for interior heaters usually. That would be your space heaters. Or there are 220 volts for larger heaters, so that would be like garage heaters. So we're looking at the voltage here because that's going to tell us how much heat it's going to put out. So this will be related to BTUs. Okay. And if you remember BTUs, that's British thermal unit. And then the higher the BTU, the more output that heater will have. So you want to pay attention to how many volts we're putting into it, and then the BTUs. So more BTUs equals more heat. Alright, so that's worksheet 1. On to worksheet 2. So we're going to be using our new equation here a little bit. So we have to pay attention if we have voltage, current, and time in the equation. That's how we can figure out how much work is being done. So this one is just volts and charge. So that means we're going to be using that formula, which is just like on the last worksheet. Okay, so if we look at this one down here, we have a voltage of 12.6 volts, current of 5.6 amps, and then we're talking here, we got some time. So when we are looking at time, amps are coulombs per second. So we want to use this one. We don't want hours, or if you see hours and minutes, usually they're going to be converted to seconds. Okay, so our formula, work equals volts times amps times time. So there's 3 variables here, 1 variable here. You want to fill out all of your table here to make sure we have everything, how much work is done, so we're looking for W. So that means we must have volts is 12.6, and amps or current is 5.6, and then time, that is 7,200 seconds. So you're just going to plug these 3 things into your formula. Alright, so 12.6 volts and 5.6 amps and 7,200 seconds. And then you just slap that in your calculator, see what we get. So 12.6 times 5.6 times 7,200, and we get, it's probably going to be a larger number, 508,032. Okay, so 508,032, and then again our units will be joules, just because we found electrical work. So 508,032. Okay, so the rest of these problems on the front page are just using your 2 formulas here. You're looking to see what values they have. So here you got charge and work, so that one's going to be a little bit different. Make sure you plug everything in correctly. Work is on the left, charge is on the right. Okay, so you got to think to yourself, how am I going to solve for volts? You'll have to divide by that, and then remember the label for volts is just volts. Okay, so here we have time involved again, so that's our other equation. So it's not too bad, plug everything in. Number 5 was one that more people had questions on. So this has a part A and a part B. Okay, so electrical pump lifts 800 newtons of water from a well 50 meters deep in 90 seconds. So we have newtons involved here. We haven't had that with electricity yet. And we have meters as well. So that's really not electrical units. That's why this first question says how much work is done by the pump lifting the water. So the pump lifting that water, that's going to be mechanical work, or we can kind of think of it as fluid work, the way we have it worded here. We have a force and a distance that we are using. So we're looking for work for this one. So it's just our equation is written there, force times distance. Okay, and the variables we're looking for, or we're looking to use, are the force and the distance. So force is in newtons. We have 800 newtons listed, and then we have a distance of 50 meters. So that's what we're going to use for work. 800 newtons and 50 meters. Just multiply those two. Well, 8 times 5 is 40, right? Then we'll throw those zeros on there. So 40 and then 3 more zeros. We'll double check to make sure the mental math is right. So 40,000, and we solve for work, which is joules. Okay, so that's our work done by the pump. And there is actually a part C to this question as well. So we're looking for electrical work. So we got work equals volts times current times time. Let's make sure that's the one we're using. We have a current, we have a voltage, and we have a time. So yes. So solve for the work again. And I'm going to just write my variables down here. So volts equals 48.5. And 90 seconds and 10.3 amps. So that is 10.3 amps, and time is 90 seconds. Everything is good, so let's just plug them in. Okay, so 48.5 volts, 10.3 amps, and 90 seconds. Put that in your calculator, see what you get. Oops, and we get 44,959.5, and that is joules. So then the part 3 for that question is, what is the efficiency of the pump? And here's your equation for efficiency. So this is the way we wrote it in class. Work out over work in times 100. We're solving for E. And then we have to get our work out and work input from our last two equations. So work output, that is actually usually output if we're dealing with electrical systems. That's the mechanical work done. Okay, so that would be our 40,000 joules. Our input, that's our electrical work. So 44,959.5 joules. Okay, oops, too far. So plug everything into our efficiency equation. We have output over input. So 40,000 joules over, oops, come on. $40,000 joules over 44,959.5 joules, and then times 100. So put that in your calculator, see what you get for that one then. So 40,000 divided by our 44,000 times 100, and you get 88.97. So we want to round to the 100th place. 88.97%. That would be the efficiency of our pump. Okay, so that one took a little bit of work just because we had to find 3 different pieces for it, but we found our mechanical work done by the pump. We found our electrical work by the voltage that's pushed through the system, and then we used those two to find our efficiency of the pump. Okay. The final part here would be just some vocabulary definitions, which you can look those up. On the previous worksheet, we looked at that one, or we thought about that one and that one. The joule, that's just the unit for work or energy. An amp, that's coulombs per second. A coulomb is the definition of charge for electrons. That's 6.25 billion. And efficiency is just how well something conserves energy. All right, we're usually talking about machines or electrical systems or fluid systems there. So hopefully this helps you out a little bit to figure out some of these problems, but we'll keep working through them. Let me know if you have any questions.